want to check out some of the talks you missed yesterday. Some of them are already in the YouTube EuroPython channel. So today we have Mike Miller. We'll talk about Python optimizations for your programs, for faster programs, right?
Yes.
Okay, thank you.
Thank you very much for the introduction. So, early in the morning, third day of the big conference. Hope everybody is fresh and fit, because we have 3 hours to fill with a pretty intensive tutorial about faster Python programs optimization. My name is Mike Müller, and I've been using Python since version 1.52, still remember, it was pretty new then, and so it's 1999 when I started using Python, and I've been training or giving Python courses since 2004, and Python Academy exists since 2006, and we specialize in Python training. Just a few questions about, maybe I just go through and then ask a few questions about the audience. I just want to show you quickly what we're going to do today. First, we have a first short overview here. The first question, how fast is fast enough? And I will talk a little bit about optimization, when it makes sense and doesn't make sense, and give a few guidelines, which are very important if you need optimization in the first place. And then we looked in some a little bit in strategy, how to do it. So we look in a little bit into PyStones, if you're not familiar with this. And then we look at profiling. Profiling is maybe the most important thing you can do before you start optimizing, because you have to measure before you do things. We will see this quite a bit. So we look at profiling. And profiling comes in 2 flavors. We can profile CPU usage, and we can profile memory usage. So we look at this, what we can do here in Python. And then we go into algorithms and anti-patterns. So that's some kind of small-scale optimization with, like using a string concatenation, lists and generator comprehensions, local and global variables, those kind of things, small tips here and there. And then we look at the right data structure, which is probably the single most place where you can gain speed, lots of speed. Actually, I will have a talk tomorrow about which is called Python's fastest in Fortran, which is exactly about this topic. So if you use the right data structure, you can outperform even the very fast optimizing compilers. Then we look at caching. So if you calculate something and you don't want to do it again and again and again, you can use some kind of caching. We look at different strategies. And then we look at a few things, how to measure and test speed. For an example, let me go an example. It's a computationally expensive example, so we kind of fabricate a case where we need to optimization, and we look at different ways to do this. So just do it in pure Python, a few ways, then a quick look at Psycho and PyPy and NumPy, just to give you a feeling. So of course we have only 3 hours, and each of this topic could be quite big, just to give you a feeling what's out there. And also NumPy, Py. And in the end we go multi-core. We use multi-processing, we use multiple CPUs, and then we do combined strategy. So that's a pretty heavy program. Usually we have some exercises, but I think we have to skip most of them, otherwise we won't fit it into 3 hours. But still it gives you some kind of an overview what's going on. Okay, so you should have gone to the website and installed those things. So there's a few things here that are like the Scapy framework is only Python 2.6 and lower, so it's the same as Psycho. So I still kept them in, though they haven't been updated, but quite a few people still work with older versions of Python. So I know big companies, even some are working with 2.4, 2.5, 2.6. It's still pretty common, so I kept it in, even though it's not very current anymore, but it can be used for the times. All the other things work with Python 2.7 also. So it just, here we also kind of skip over those things quickly, but there are still things in the material. And those other things you should install. In addition, you can download the course material here at pythonacademy.com. Download your EP 2012 optimization.zip. And this contains the PDF, which is a handout. So we didn't get it printed for some reason, so you can use the PDF. And then also the source code for all the examples, so you can see what's up there. So the website is still there, and just download it and unzip it. In the beginning I will talk quite a while, so you have maybe half an hour until you need the material, so there will be still time in the beginning of the course. Okay, I would like to get a little bit an overview of the audience. So who of you is using Python a year or less? Yeah, just a few people. 2 years? Okay. 5? Yeah, it's kind of majority. And more than 5? Yeah, it's about 20%. So, okay, it's pretty. So we have people from all kind of core levels of how long you use Python doesn't mean too much, but at least gives me some indication what to expect. So, if you have any questions about things, please ask. So, if there's something unclear, I will try to explain if it makes sense. Okay, so let's look at this thing. I have the handout. So if you unzip the thing, you should see something like this. So if you unzip it, you see a directory code, and the other one is a handout. And we will largely work with this handout because it's like 75 pages, so it's quite substantial, and you can go through and work with it. So that's a handout, so you can always read along, and the handout is not just bullet points, it's real sentences. So yeah. Yeah, so the link, that's a link. So Python Academy download, EP 12, 2012, optimization. So unzip it, and then it's not a big, it's just a PDF and a few Python source code files. No, it shouldn't be too difficult. Okay, so let's get started. And I just go the first the motivation. So that's a content again here. We're going to go through. You see, it's about 75 pages in total. And a lot of people say Python is slow, and I don't really disagree. It very depends on your perspective, what you're doing and what slow means. So if you do numerical calculations, which I also do a lot, then Python, it's kind of slow because there's a lot of overhead doing numerical calculations. But for many other things, Python is not slow. Actually, it's pretty fast. And therefore, it's a question, do you need optimization? And to do this, you have to know what's going on. That's the most important thing. Just don't start because you have the feeling you need optimization. To optimize, the most important thing is the first part we do here, to ask yourself the question, do I need optimization? And therefore I have a few optimization guidelines. I want you to keep this under your pillow. So premature optimization is the root of all evil. That's a quote by Horry. And I think that's very important to know this. Premature optimization is the root of all evil. Before you start optimizing, you think about your problem, and then also you measure. That's the next thing we go do. We do profiling, and profiling is the single most thing you need to do before you start optimizing. So you see where things are slow. So the first thing is you have to make sure your program is really slow. Is it really slow? And this is something you need to answer yourself. Do you really need the performance to make it slow? Your program might be slow relative to something, but in general for your whole application it doesn't need to be much faster. So something, if you like have a GUI program, the GUI program is waiting for the user input most of the time. It doesn't really matter if it waits for 0.1 second or 0.01 second, because the user cannot see the difference anyway. So those kind of things you have to make sure. Do you need optimization? Unless you want to do an exercise in optimization, just try yourself, because optimization can be quite a bit of work. So you really make sure you need it, and also you have to make sure that Python is a bottleneck in your application, because most of the time application is not only Python code. There's a lot of other things going on. You interact with the operating system. You might do file input output. You might work with a database. You might go through the network. and all those things might be way slower than your Python program. So you can optimize everything out of your Python program. Your program in the end won't be any faster because other things are the slow ones. And that's very often the case. So make sure you really need the optimization. So we will do a few things on this one. Don't optimize as you go. That's a pretty bad idea. So you should make it work right before you optimize. Don't think now, oh, this could be faster, and I just have this gut feeling and I write 10 extra lines to make it faster. That's what I mean. Don't optimize as you go. I like the optimization. Python offers a few things where things are shorter and more Pythonic and faster. So that's my preferred solution, and I will show you a few things. So most of the time, if you use built-in things in Python, things are faster. Not always, but most of the time, and also better readable. So that's a nice place to go. If it's better readable and faster, that's good. If you need to put extra effort to make it harder to read and harder to maintain, then it might not be worth it. So, and don't do this as during programming. Do it afterwards when your program is running and is doing what you want. And only use realistic use cases. So if you write a small script that's just run by a few people a few times, you don't need to check test cases to run it 10,000 of times or something like this. You have to have some kind of realistic use cases, what you want to use your program for, and don't fabricate things that are not there. That's sometimes happened. Also, architecture is important. Architecture can be seen as an algorithm in the higher level. So how do you set up things in the first place? Though it's not necessary before the Python things are slow if you set up things in the wrong way. So that's something I cannot give a good example. It depends very much on the application. But you have to check this one. If you do profiling, you might see that architecture might not be right if things are slow at certain places. Though, are there any bugs? So that's the first thing. You also have tests and see if everything works right. Sometimes bugs make things slow. So if you do something, and this is the famous thing, people forget to sleep in the loop, and everything's so slow. Yeah, and then you can profile optimize as well. You want to have to just make it work right first. If it's really slow, though, it's a profiling. We'll do this. We use cprofile here to profile things. And also, you should always check the optimization results if the results are the same. So that's easy because sometimes optimization makes your code more difficult, more complicated, and you might introduce bugs. So that's the thing you don't want to do. So other things I said already. So if you work with a system, network connections, database access, this can be much slower than anything you do in Python, and you check this first. So that's the first thing, and you will see many cases then you won't need optimization at all because there are a lot of other things you cannot optimize, at least not by improving your Python source code. Maybe improving other things, maybe reducing the number of times you need to access your database or do system calls, optimize in another way, but not necessarily write faster algorithms in this case. So, and sometimes it's just easier just buy better hardware for things. It might be easier than spend a lot of time on optimization and make things more difficult. So that's the first thing you have to keep in mind. And I think there are a few talks here about optimization. And I think that will be very similar in terms of what's going on. Okay, so the first thing you can do, you have to measure things, and there are some different strategies for measuring. So for everybody who came late, please download this thing from the website. That gives you the handout and the source code. And the next thing we want to do, we want to measure. So that's maybe the most important message to take home. Measure. If you don't measure, you don't know what's going on. So very often have the feeling that's like this, but the feeling is just plain wrong. Even though I have experience, and it has been like this in many other cases, but this case is different for some reason, and you just don't see it, and if you don't measure, you don't know. So you need kind of hard numbers to measure things. And there are a few ways to measure things. The first one is the PyStones. So there's who knows about PyStone? Just a few people. So PyStone is a test that comes with Python. It's a benchmark. The benchmarks are always kind of benchmarks. You know, they are talking to measure something, and they're not perfect. So a benchmark is never perfect. Depends who is doing the benchmark. You can tweak a benchmark whatever way you want to get your result. But this Python benchmark comes with every Python installation, and then you should be able to run it on your system and see what's going on. So if you just open a Python, you can run it from your system, and it's under lib test. So if you wherever your Python's installed, you can run it under lib test. So if you just open a terminal, and you should go to, I think it's library. Just it depends where you have things installed. Framework. So it depends on the machine. You should. I think I'm not sure. But it's pretty. I have it in framework installed, and it's Python framework. Just the path is so long I don't really remember, so I just go step by step. And under the 2.7, and then lib side packages. No, lib test. Sorry, lib, and there should be a test, another one, Python 2.7. So it's pretty. Yeah, so it should be. No, so I'm in the wrong directory. So you should have the. Should have this Python thing. Yeah, cd lib should be in lib, and then in tests. Okay, test. There we go. And then if you look in test, there should be a Python. Python .py. Yeah, and this Python.py you can run, and you get some kind of benchmark for your system. So depending on your operating system, will be a different place in your Python install, and then you just can run it, Python, and then you see some kind of two numbers, and see it's a Python 1.1, and you have two numbers. You have a time, and you have this one has 69,000 Pythons, 69,000 Pythons per second. So, and you can try different installs. If you have different installs, so like I have PyPy installed. If you try the same thing with PyPy, then you get a different result. So with PyPy, I get 430,000 Pythons. So obviously the PyPy people know this Python test, and they optimized PyPy for it. So if you might add some other kind of test, PyPy might be a bit slower. So there I have some cases PyPy is slower than CPython. So it's not clear cut. It's every time it's faster. So I tried different versions of Python and different things. So I have it written in my thing here. So if you do this and you try different versions here, see it's also Python 1.1. It's a different machine though, but you see it's Python 2.5, 2.6, and you get quite a bit. So 2.6 is obviously quite fast. It's the same machine here than 2.5. 2.7 it's a bit slower for the. So it doesn't say a lot. It's just benchmark, but it gives you some kind of feeling how things go. And if you run it with EuroPython, which is of course a Windows thing, unless you use this mono thing. So I run it on the Windows with EuroPython, and this is about nearly twice as fast as CPython, not quite 100,000 instead of 60,000. So it's quite a bit faster. And if you run it with JSON, this is an older version of JSON. Here, sorry, that's PyPy, and PyPy is going with 300,000. And if you go with with JSON, then you're quite slow. And you will see if you rerun this test several times, you might get different results. Especially if you have everybody has a laptop and they have like energy saving functions, and the first time might be much slower because it's kind of going to wake up or something. There's a lot of other things going on. There are not only Python and how things go. Most of people now have multi-core, everybody. So it's better because before, if you have only one core, then other things might go on in the core, and this one kind of interferes with this measurement. So Python gives you some kind of feeling how things go, but benchmarks always have to be taken with a grain of salt. They're not perfect, but they give you something. You can also use it interactively. You can just import Python and run it interactively and do things there. So you can say from test import Python and run Python interactively. So if we do this, I just open IPython here. So I think I work with IPython, which is gives me a nicer interactive shelter. If you have it, it's fine. Otherwise, you can use a normal Python prompt. IPython is fully compliant with Python. Just gives you a few more things. You can do things like this. You just can do shell commands, and the help is nicer. So from test import Python, and you can then do this. So please don't create a package test in your current directory. That happens frequently. People like the word test, but test is a part of the standard library. And then you can use Python and run the Python. You should get a similar result than on the command line. So it gives you the time. And if you rerun it several times, you will get slightly different results. Yeah, so it's very close here. So obviously, because I started it up already, so you see it's quite different. 59 and 64. It's a few percent. It's more than 5%, 6%, 7% difference. Okay, so that's one thing you can see, and you can also kind of compare between different machines and different implementations of Python how fast things are. There are other benchmarks, and they give you, every benchmark is stressing something else, and a lot of benchmarks they try to be kind of cover a lot of ground, but it depends on your use case. Then this benchmark might be good for your use case or not. That's difficult to do. But at least there are some, and it's kind of something people settle on, use this benchmark. Okay, so I have a few things. So I wrote a small helper. So if you go to the now open this. If you go to the directory, I can do this from here. Go to the directory and see that's there's code, and you go to code, and inside the code I have several subdirectories, and the one we measuring, and inside measuring we have quite a few Python files there, and one of them is it's called Python converter. So if you look inside in Python converter, and you should see this Python code here, and it's just a small helper that converts your Python from seconds and multiplies divides by 1,000. You get a kilo Pythons. Because numbers are so big, are kind of difficult to read. I just divide it. So that's just a small helper that converts from seconds to seconds to run. You get the because you run the Python test up there. You see, you get the benchmark time and your Pythons, and then you can, if you run your tests, you can convert them to kilo Pythons. This gives you some kind of measure, some kind of thing. If you run the same algorithm with different machines with different Python implementations, you can kind of abstract those things away, because now you get some kilo Python things because you multiply with a Python you get from your machine. This is machine dependent and implementation dependent. And then if this is a runtime of your program, you kind of normalize to a certain degree what's going on. So this is some of those small helpers you can use to do things. Okay, so now let's assume we would like to find out if our program is slow and where it's slow. The thing to do is profiling, and Python offers a few tools for profiling. There's a built-in profile which is written in Python, and it's not recommended to use because it adds a lot of overhead. So every time you measure something, you influence your system. The question is the influence you put in your system significant for your purpose? And that's a very difficult question, because per default you cannot tell, because as soon as you measure influence, and if you don't measure, you don't know. So it's kind of problem. So you have to try. The only thing you can try different techniques, and they have different impact on your system somehow. That's something you might be able to do. So there's a one. There used to be a profiler called Hotshot, but it's not recommended. We should use cprofile. Cprofile is in the standard library in Python. It's written in C and has much less overhead than profile. So that's a profiler we should use. And just go to the this directory, and in this directory we will have just open it from here. That's the easiest. Okay, I just open the file. Now I would like to profile. Can I just go up here? Just want to go to the directory. So in this directory, in code, in measuring, we have this test program called Profile Me. Profile Me, and it's a very stupid small program, but it should make the case. So that's just this very small program. We import time to get get sleep, to get things to sleep, and I just write two functions: the fast one, which waits for thousands of a second, and the slow one, which waits a tenth of a second, doing nothing else. And then I use two other functions that just do so on. And this one calls slow 100 times, so I do it with xrange, which is a recommended way to do in Python 2. Use xrange if you don't need a list. And I have a fast one doing the same thing, calling the fast function, and then use both of them. So that's my small test program I have, and now I would like to run them, and I can do it interactively. So if this one is in the directory you work with, you just can do it interactively. Now I've changed in this directory, and I can say import profile me. So now I have profile me, and now I can import a C profiler. So everybody should have C profile installed because it's in the standard library. And now you can make an instance of. But you can read this, yeah. Maybe I move it up a bit. Okay. And now you can make an instance. You say, yeah, call it profiler, which is I use C profile. I make an instance of this class profile, and this one I can use actually to do several things. For this we too many profile ones. Run call profiler, I called it profiler run call. You see it has several run functions here, and I use run call. Because run call I just can give it an instance of the class I want. I just give it a class object. It's the class object. Profile me, it's my module, and inside I have this use fast. And I don't call the function, I just give it, it's different. I don't have opening, closing parentheses, I just give it the object and tell the profiler please run the thing. And this takes a bit, in this case is fast. And now we can look at the statistics these things produced. You can look at profiler, and the easiest way if you're into active work is print stats. You can also save all this. It's more common if you do more profiling to save all the information in files, so you'll see how you can do this and look at later on. But here now we just look at the stats, and it tells you, okay, I called, it's ordered by a number of calls and the time it takes. So I call this function use fast once, and this one, and 100 times the fast one. And then here's some overhead. You see disable of it's a method that's from the profiler. So you see already that the profiler is kind of measuring itself a little bit here and there. So it influences the system and shows even up in here. And also you see where the time is. The sleep function is taking the time here, and then you have it per call, and in total you see this per call is very little, and this one 0.118 and this is 0.119, so this is pretty much the same time, so every time is in the sleep here. So this is a very simple example. If you run a bigger program, we can get a very long listing. But most of the time, you're only interested in the functions that already take a long time. So you will, and very often you have this. You have some kind of a bottleneck, and you see which function gets called a lot and which one takes a long time. The problem if you measure functions that are very short and called a lot, then your measuring overhead is big compared to the time it takes a function to run. But since you also measure the function that calls a function, then you see pretty much what's going on. But it's also not correct, because you have to go into code with the profiles to go into code and measure the calling, and then it's changing the execution time of the function. So it's always a little bit difficult to really get a good measurement. Okay, so that's the first thing you can do. Let's do the same thing. Instead of fast, we go for the slow one. So we run it. It takes a bit longer. See, because now everything takes 100 times longer. So if I press enter, it should take a few seconds, and then you can look at the stats again, and you see now it kept the stats from before. It's kind of accumulating, so it still has what happened before, but it adds now this slow. When you see the slow one takes about 10 seconds. Yeah, that's pretty much 100 times longer, 0.1 to 10 seconds. That's pretty clear. It takes much longer because this function doesn't do a lot; it just sleeps. Yeah, that's clear. So you get some information, and you see you have number of calls, the total time per call, and the cumulative time. So you get some statistics there about all these calls. Okay, this is the first version, so you can use run call and give it a function object, as we did here. A little bit different variation would be to call profiler run, and now we don't specify an object, we rather specify a string that will be evaluated, that will be executed, and you can just type what you would like to execute. In this case we do fast. In this one, fast, we actually call the function, because it's not an object, so we actually have to use the parentheses there to call it, and then you should get use fast, sorry, not run fast, use fast, and then you should get the same results. And if you look at the stats again, it should be now called 200 times. You see now it's 200 down here because it's accumulative. So this is one way to kind of explore interactively things and do things. You could also, if you don't want to do this interactively, you could, because this is just some explorative things, you could also add this to your program, and instead just doing like this, you could have a second optional argument, which would be a file name. So you just provide a file name, and this one will store the results in this file name. And now you can do the profiling once, and so somehow run fast. It takes exactly 3 given. Where's the third one? Ah, yeah, sorry, yeah. It's C profile, not the instance. I have to say C profile. It's a bit different. C profile run. Okay, now, sorry. So I don't use the instance, I use the function run. And because this, obviously, if you have this one, it's always a problem with using a method and a function. And now you can have an optional third argument, and this stores the results in this file. You could look in this file, but usually you just use some tools to read this file. And there's a built-in one. It's called pstats in Python. pstats, and this pstats helps you to interpret what's in there. So you get your stats, and you use a module pstats, and inside pstats you have the class stats, and then you just provide the file name. The file name again. So the extensions is kind of convention to use it. You can use whatever you want, of course. And now you have this object, and now you can run several kinds of analyzers on the top of it without rerunning the profiling again and again. So DC has a lot of different methods here you can do, and you can call this, and you see this now is the same thing we had before. But obviously you can fortify your code with the things and save the results in different files, and later on you can look through and look at things, and you have more tools, not only the printing tools. You can do different things. For instance, you can sort things. So you say stats, instead of print you say sort, and you can sort by you see you have different things you can sort, and in this case we say sort stats, and then you can provide the name of the column you want to sort by. In this case I say called. You can also use the others, how many times it's called, and then just print stats on it. And this one should give you, and you can also limit how many you want. I just want the first 3 in this case, and I get only 3. So if I would say 5, I would get 5. Yeah. So this is several tools you can, and it helps you to go through. You don't have to write it yourself and go through the things. They help you to look through what you can do. You can also get information about callers and callees, so you can say who called whom. Those kind of things that can be done. So stats, and you just say print callers. So you see who called whom, and print callers, and you say, okay, I would like to have who called fast, and then you would see that who called, where the calls appear, what happens. Use fast is the fastest called by use fast. You see the arrows, who is calling whom, just because now it's breaking here on my display. So you get this when you have the same thing, the callees, the caller and the callees, you can, and you say just use fast, so you see that's the other way around. You see, okay, this use fast is calling profile, the arrows in the other direction. So you get some kind of information what's going on, who's calling whom. You can sort by all kind of things and do things. Okay, that's very nice, but this is everything is just just tables and a lot of numbers, and sometimes it's difficult to grab if you get a very long list of numbers and you want to see what's going on. But there's a tool which is very nice, which is called Run Snake Run. It's written by Mike Fletcher, and this is a very powerful tool to visualize what's going on. So if you, it was on the list, so if you try to install, you have to get WXPython installed to get it to run. But when you have it installed, so now we have our stats file we just created. Yeah, this fast stats here we just created, and this one can be used now. The same output can be used with this Run Snake Run, and to visualize what's going on. So you just, if you have it installed properly, you just say Run Snake and give it a name. Give it the name of the file you would like to visualize, and then it should give you. It takes a while and starts up WXPython, and you can see here now we have this. This table is the same information we just saw. So you have all the information you get. This is textual output, but in addition you see you get those nice rectangles here, or yeah, rectangles nested each other. You see very, very obviously most of the time is spent in sleep. If you use a bigger program, you will see a much different picture with different colors, with different boxes. Because this is so simple, then you see how all the calls were everything just calling each other, and then everything ends up in this sleep function here and takes so much time. Everything else takes much less time. And if you go over here, you see it's going to highlight where you are. So that's a very nice tool. That it's very, very useful because you have a very quick visual impression what's going on. So everything. So this needs WXPython installed, and I think also OpenGL, I'm sure. So it takes a bit of time to install, depends on your operating system, but it can be very useful. So if you do this, then you get some information what's going on. Let's look at a few others. I ran a few other programs through here and made some graphs. So that's our sleep here. And if you run another one, you see now here, this one has different boxes with different kind of things. And this one, this is a other version with we use NumPy. We use later on the course, we use NumPy. And you see that looks different because NumPy is doing quite a bit in the background for you. And you see this picture. And you see it's not that clear where to optimize. So if you have something like this, it's pretty clear the big one you want to go for. You want to go for this big square, and you want to optimize here because you probably can get the most here. It looks like this. This is still big, yeah, but it's not. It's less in it. Just like the import is pretty expensive here. NumPy is doing quite a bit in import, so it takes quite a bit of time, obviously. But the init here, all these importing things, it seems like one of the biggest blocks, and there's some other blocks doing here, and a lot of small ones. And those import is nothing you can really influence without changing the library. So that even if it's a big one, so that's NumPy. We look at NumPy later on, and you're usually not going to change NumPy if you want to make your things faster. That's a third-party library, and it's very unlikely you're going to change it. And if your algorithm is somewhere, whatever happens somewhere in here, then it's pretty difficult to decide what you're going to do. You can try a few things how to make it faster, but it's unlikely that you can do a lot. Unless if you have something like this, everything is written by yourself, then you can go in and try to optimize things. Okay, this is profiler, cProfile. cProfile is very useful, but you've seen cProfiles can only profile on the function level. So you can only see how long it takes to run one function. Sometimes you want to go into more detail, especially if you have lines in your program that are not function calls, but can still take very long, so you cannot get finer resolution than your function call. But there's one profiling tool in Python called Line Profiler. And Line Profiler is very interesting because it helps you to go line by line. But you have to take it with caution because this is written in Python and has the same problem as Profile that adds a lot of overhead. So for certain problems it can be useful. For other problems it adds so much overhead, then the measurement is very difficult to read. It's very useful if you really if you work with NumPy. NumPy you do some assignment, and NumPy is doing a bunch of things behind it, but it's not a function call. So if you don't want to change your code to change every line in a separate function call, you cannot use cProfiler because you cannot measure it. So then line profile might be good. So if one line takes a long time anyway, and is spent somewhere else, then Line Profiler can be useful. Because if you do NumPy, it's run in C anyway, and Python cannot go into C. So it's one big thing it's happening in C. So you can use Line Profiler, and now we can run the Line Profiler on the same thing on this profile me. So we'll go back to the shell. I just probably close. Where does it go? I'll close it properly. Yeah. I'll close the thing. Doesn't seem like it has. Yeah, that's it. Okay. So, and I just close this program. Okay. So if you have Line Profiler, you can just pip install Line Profiler. and it should install. It has some C functions, so you need a compiler, but depending on the operating system, it should be not that difficult. So once you have installed line profiler, you can use it the same way as you can use profile. The name, the call is Kern Prof. So the line profile is written by Robert Kern, and so he gave his own name to the profiler, and then you can just use it, and now we can run it on profile me.py, and it's doing the profiling on this profile me. So this takes quite a while because it adds some overhead. So instead of this 1 second, it takes about 10 seconds here, and gives you, in the first place, it gives you the same view as C profiler. But you can also add a few decorators, or actually one decorator. And this one decorator, that's a profile me use line profiler. This is this program, yeah, this one. And see, it's the same program. The only thing I do, I add this profile decorator here. And this profile decorator, it's a bit of a hack because this is injected in the built-in namespace. It just appears. So it's obviously only for your profiling. So if you can turn it off easily, you just write your own. I think there's even mock there, just doing nothing, just profiling plus decorating a function doing nothing. You can turn off the profiling. That's pretty easy. And so I do this, and if I do this now, it's the things I get things line profiled instead of just going and getting it profiled by the function call. I can do this, and I just run this, and it doesn't work. Yeah, so I have to call it with the option -L to turn on line profiling. If I don't do this, it gives me an error message. So, and if you call it with -L, and now you saw the one before took about 10 seconds. This takes longer because now it's going in and checking every line and profiles. You see, now I get a very detailed description what happens, and it shows me the source code for all the functions that I decorated with a profile, and shows me the source code and the lines that go with it, and then how many times it's called, and the time per hit. So you see everything. This is not seconds, it's different unit. It's microseconds, I think. Yeah, you see. You can see how much time the loop takes. That's a loop, the for underscore in x range, and then how long it takes to call this function and compared to this. So this gives you a line by line description. So I have a few other function that I want to test with my line profiler, and I do a few things here. So maybe I just go through. Yeah. So we have a function, a module called accumulate, which is doing something we want to measure. You see here, this is accumulate. This is a function in NumPy. You have it, for instance, and this is doing nothing else but kind of saving the intermediate results. So if I say accumulate range 5, the range 5 are the numbers from 0 to 4. So 0 is there, 0 plus 1 is 1, 1 plus 2 is 3, 3 plus 3 is 6, and 6 plus 4 is 10. So it accumulates all the sums when I sum up things. So that's what accumulate is doing. It's the same thing for 10. So it's accumulating those things. And this is just the program I wrote, and actually deliberately you could write this much faster, but deliberately I put it on to different lines to see how much it takes just to access the last item, and how long it takes to add them, and how much time it takes to append. You could do everything in one line; it wouldn't be a problem. But if you do it in one line, obviously you cannot line profile it, and then you add the line profile decorator, and then you run these functions with 10 and 100, and then if you do this, you can see what happens. So we do the same thing, but instead of this profile, maybe just use accumulate and see what happens. Accumulate, and you see now it gives you a pretty detailed overview what's going on. And I think I have to make it a bit smaller, otherwise it's difficult to read. Yeah, still? Okay, so maybe still readable. So now you see it shows you what time it takes, and you can see here it's pretty evenly distributed. This is the percentage of the time. It takes about 20% for each of this line. So it's all of them are pretty evenly weighted. So the addition takes about 20%, the append takes about 30%, and this access takes about 20% of the time, and this loop here also takes about 20%. Yeah, so that's you have a pretty good overview, and you get a feeling how long things take. So they are all pretty the same time, about 20 to 30% of your whole time. But this can be pretty interesting. Good. And then I have another small example that can be helpful doing the mathematics, a little bit mathematical things. So this function is square calc, I think. Calculation. Yeah, this is just also again a loop, and I just, in this case, I just here assign. Of course, I don't assign square SQRT to mass square, so I don't have to look it up all the time in the loop. It's a kind of optimization already. And then I try different things, plus, multiplied, power, and I use the power operator and see how long things take in square root. With the access to the module name, the fully qualified, or use the local variable, and then just access those things. So a few things just to see what happens, and if you run over it, you get some feeling how long things take. Okay, so if I run this, it takes a while, so I can make it bigger. Of course, I still have space. Okay, you see now, it shows you how long things take, and it's very obvious. If you look in here, the power operation is expensive. So if you use power, it's expensive. So most of the time I use like square, I use like x times x instead of x power of 2, which is usually faster. The power operation is expensive here. And you can see if you use the square root and you access it directly in mass, it's a bit slower than doing it just like this. But compared to this one, it's not a big difference. Yeah. Then if this is just the access. So if I access the names, the local name, and this is the name through the module, there's a bit difference in time here. Yeah. Yeah. I don't know why this difference is bigger than this one. There shouldn't be a big difference, but it's doing the same. But you can see, you get a feeling what things were. It's pretty useful to do, but you always have to be careful that things introduce some overhead. And yeah. So I have a few more tests here you can do. Another one is local names. This one what I did here already, I have a little more sophisticated. So I can test the access to local names, local references, and yeah. So this is just a so I added a few things. So like if there's no decorator profile, I just make a mock decorator. So if you're familiar with decorators, I just define my own decorator, which takes a function and doing nothing. Just takes the arguments, calls a function, and returns a mock. So this is just kind of a really mock. So I can run this program no matter if I want to run it with line profile without or not, and doesn't add any overhead. Yeah. No, you have to call the function somewhere. Yeah, yeah, you're right. Yeah, yeah, this would be even easier. Yeah, because I'm used to this. Actually, yeah, you just return the function. yeah, this would be, yeah, that's a good idea. Just say, yeah, so just like do this. Yeah, great, yeah. Make it even easier, just return the function and do nothing. So, but wouldn't, yeah, so it would be even better, because now the decorators run at compile time and doesn't add any overhead to your program. It's just run once and you compile the bytecode, and then it's just the function here. The only thing you would like, yeah, this one you don't even need to change the names or anything. Great, thank you. Yeah, so this is just a mock I used here, and if there's a problem here, I just define the mock and do this with a mock. And now I have these two functions. One has a local reference and one has a module reference. You see here I just have this, what I did before, and I just use this sqrt, and here I use the fully qualified thing. And then I have just this a function here that I also profile, which is calling those two functions. Yeah. So we see how things work. So if I run this one, local reference, then takes a bit. Maybe I did it too often. And you see the differences it has when you do it. Still running. Maybe I chose the bigger number. Likely. Yeah, just 10 to the power. Let's kill this one. I think I changed the source code and put a bigger number. So just go and make the number smaller. Don't do it 10 million times. Just do it 1 million, 100 million times with 1 million times. That should make it a bit faster. Okay. See, now we have a result, and you see there's a bit difference, and the problem is here that the difference is not very big. It's pretty close, and in reality the difference is a bit bigger, because we will see this one, because you have to look at every line, and it's called a million times, so all the measurement is also called that often. And the measurement in this case takes longer than the access to this name. So if you do this differently, so if you don't run it, with the L, there's the same one, I just don't use a profiler here, so now it's using my mock profiler. Now we can prove it works. And now you see I'm doing the same thing, and this just kind of falls back to C profile. It's the same thing as C profile in this case. So this clone prof is just a runner for C profile. And now you see the differences here when accessing the local and the global one. So this is the local, and the module one. You see this one is 0.04, and this takes about twice as long. So the difference is much different. This looks very similar. It's like about close to 50% for each. But here, the modular reference takes twice as long as just using the local one. So yeah, say 50% of the time, or 100, depends which way you want to look. Yeah, and this can be substantial. We can make it twice as fast, at least this part. But the line profiler doesn't show me this because I introduce so much overhead measuring those things. So I communicated this with Robert Cohen with this, and he says, yes, that's overhead. That's unavoidable. So as soon as you start measuring, you introduce an overhead. So you have to be very aware of it. What you measure might not be the reality. You measure your measurement. And there's no real way out of it. There's to do this. Yeah. So that's a problem. You have to be careful. So up there you don't see it. So if you put it in a function, you see a better picture. Yeah. So because now we can boil it down and see it. And this function takes longer. And if you have something like this, then you might need to rewrite your code just to measure and put everything in functions and try to isolate things in a way that makes it easier to measure. So that's just some things. Okay, good. Again, measuring is very important, and so far most people are concerned making programs faster, and you want to profile your CPU usage. Another use case would be profiling your memory. And profiling memory is also not that easy, and there are a few tools out there. And I would like to show you the first one, which is called Heapy or the Guppy framework. Unfortunately, this is only Python 2.6 only, and I think this guy did it in his master thesis. And they changed something in the API in 2.7, and he hasn't updated yet because some kind of C function is missing and you get an error. So you can install it and you can import it, but as soon as you execute it with 2.7 you get an error, which is unfortunate. But it's still there and it might be updated. That's why I kept the material in. So if you're interested, you can use it. So it's pretty easy to use. So you can... So if you have 2.6, you can install it and try it. And this Pylon as scaled double just gone, and this breaks the whole thing. Okay, you just can import it, and then you make it's called a heap. You make an instance for a heap, and you can look inside your memory, and you get an overview of what objects are there and how much memory they use. So in this case, they have so many strings, 27,000 strings, and they take so much memory, 1.5 bytes here, 1.5 million bytes. So you can see the size and how the percentage. So that's something you can do. And there's about 150 different types. So Python has a lot of different kind of, you see, look at dictionaries, and not just a dictionary, different kind of dictionaries here and whatever. So you can get quite a bit information. So if I create a big list with 1 million elements, and do it again, and now, of course I have 1 million integers now, we have so many integers, you see it's about this, more than 1 million integers here, those are integers that had been there before, 1 million integers, and they take 95%, yeah, oh, that's 95%, and that's a size here, and 60% of this memory of the total. And then the list itself also takes space, because the list needs to have space to put the elements inside, and you can see how much space, how much memory it takes. So, and if you delete the list and do it again, then you're back and the things are gone. Yeah, and then we can do something interesting with setref. You kind of clean the measurement, so you set your measurement to 0, and if you do this heap again, then you get something close to 0. There's still something left, but very small, so that's something, that's a measurement error. So you can set it to 0, and then you can allocate your list here, and then you see now the list, the integers in the list take 99% of the space. In 74 and 25 is 99%, the rest is an error. So it's 1% error in this case. But you can see how much memory you need. And that's usually the way you set ref. So you go back and then you do something and you can see the differences in memory. Memory changes. So if you do heap, you get this memory changes. And this object, what you have for the heap, has a lot of information about the size, and so has, if you attribute access, you get the size and other things. So you can get information. So if you go back and set ref, you back to 0 and see that the size is very small. It's the same thing without this big table, and then you get this thing here. So you can set back. This is about as close as you can get to 0. That's your 0. Yeah, and there's a lot of information in there, so you can access it, and you can use access it here like a list with indexing, and then you get information of the first line, and you can by type, you can sort things by type, and so on. So there's a lot of things you can do here, and also it can show more, and a lot of things you can sort by referrals, and a lot of things you can do with it. Okay, so since it's kind of old, and I haven't seen anything that's going on since 2009. There hasn't been any activity, so we just go over here, and it's just for reference purposes. Okay, the new one, an interesting project is Pimple. Pimple actually is a project that has its roots in 3 other projects. Those 3 other projects here, and they kind of come together, and it's serving a very similar purpose. And you can measure memory. So you can do this, and you can just, if you have Pimple installed, you can import a tracker, and you can measure your memory. So if you have this, you say from Pimple import tracker and measure your memory. Pimple import tracker, and then you can have this, I call it just T now here, and you have different kind of trackers. Just make an instance of a summary tracker, and then you can get some information about your system. Printf gives you the difference of the memory. It takes a while here. Obviously, because I run an IPython, the IPython itself introduces some overhead. And see, this is supposed to be 0, but there are still a few things there. If you call this thing several times in a row, this should get fewer and fewer. Because IPython is doing something in the background, there's always some memory usage. And obviously, there are some negative objects. There's obviously, it's not really accurate. There shouldn't be negative objects. So if you can keep calling this for a while, and probably you have to do it in the normal shell, because IPython is doing something in the background and using memory to do this. Okay, I have a small script that helps you to measure memory. So this is one is you can do interactive work and explore things, but very often you would like to kind of measure memory in your program. And I have a small script that helps you memory size. There's a hippie version and there's a Pimple version. This is very similar. Yeah, does it open it? Yeah. Okay. So what I do, I use a decorator to do this. So I use func tools that helps me to write a nice decorator. I use the tracker, and I use a global dictionary that will be. I will store my measurements inside. So I write this function measure memory, which is a decorator that takes a function, and then I use func tools reps. If you write a decorator, you should always do this, because func tools reps is using the name of the function you want to wrap, and also the docstring, so you don't get the docstring of your wrapper, but rather the function you're wrapping. And then I have this measure memory, which takes arguments. And now it's really necessary because I do something. I make an instance of the summary tracker, and then I run 5 times this diff thing just to get it back to 0. You have to run it several times to really reach 0. And then I try to call my function and return my function, and finally I just store in this global dictionary. I store the function has an attribute name with double underscores, the under name here, and then I can store my measurements in there. And this would be the usage the function has. See, it looks strange because I return, but since this finally will be executed before the return is guaranteed. So, and then just return my decorator. So I can use my decorator as a test. Just use my decorator to see how much memory this function uses here, and you can do this and run this this function, and it prints out how much memory it uses. So if I say Python, what's the name? Memory. Name. Memory size with Pimple, and then it's going to measure how much memory this takes. It takes a while because now we introduce quite a bit of overhead. So this one you cannot use to measure the runtime for sure, this decorator, because it introduces a lot of overhead in terms of runtime. But yeah, so it still takes a while. And now you see, okay, and I kept it this way. You get the name of the function, which is the underscore function name here of the function, and then you get what's in there. So the list, there's one list with this size, and there are about you see, that's just a reference to the integers. We said we want to have 1 million, and we get 999,800 and a few, because in Python, in CPython, at least all the integers between -5 and +256 are reused. So you can see, I don't know if you're familiar with this, because integers are mutable, so you can reuse them. So if the easiest thing in Python to see this is in CPython, get ref count, and you get ref count to 1. You see, there are 4,800 and a few references to 1. So there's a lot of references to 1 and 0. They are reused. It's just references. And if you use bigger numbers, like 1000, you only get a 3. There are only a few references because they don't share references. Those low numbers share references. But this is implementation detail. It will be different if you use EuroPython. The range is between -1 and +1000, at least used to be. And so that's why we don't get a million. So because it just counts this one, so it's a few. Because all those small ones, they don't appear again. So you see, that's what you have here. And you see this how many you have and this size. So you can store those things, what happens in your function. And I kept it just how this diff returns just a list of lists, which can be nice because you keep the type information. So if you wanted, you can also just sum up the size here, go through and just sum up the third element and see what's happening. Good. I have a very similar one, is 2 measures to fortify your code, and this is measure memory growth, how it grows. As Pimple, and you can look at it. It's very similar. Again, we write now in this case we don't write a decorator. In this case I write a function, takes a function as first argument. A little bit different approach. It can be also useful because for this one you don't need to go in your source code and decorate it. You just can use it to call any kind of function, and it's doing very similar things. It just calls a function and then returns things. And now, in this test case, I do a few different things. I call this function that just returns a list, and then I have this function called grow, which works on a global. In this case, for this, is inside a test function, but it's a embedding scope, so it's like global. So this is modifying this data, and you see the difference because this function just returns numbers, and then the function is gone, and the function itself shouldn't take any memory anymore, do anything anymore. But here, this one is changing this one and appending something to this function. This might be sometimes, if you look for memory leaks, if you change data structures outside of a scope from a function, then you might get some effect because the function is gone, but this object is still there, and it might what you want, might not what you want. But this can help you to, if you have such effects and things, the memory is growing over time, but you don't want it to grow over time, then you might have forgotten you change some global thing and you don't delete it, or it's still there, and that's what this just some makeup to show you how this works. And now I use this function check memory, which just takes the function itself. So I put on the function make big up there and grow, and then also the size is the argument. So the size is the argument that goes in args here and will be handed through to this function, which is the function we put in. So eventually number would be the size. This number is the size, and this number is the size here. We would put it in, and we call those functions. And then this one is just in this case gives us the measure diff and returns this measure diff. So actually we don't care, in this case we don't care about the function result, we just care about our measurement of the memory. Okay, let's do this. So instead of size we use growth, and we do this. And again, it takes a while because we have to do this 5 times, going back to 0. See, and the memory of the make big, there's no memory usage because the function is gone, and all the memory it used is empty. There's no additional memory usage after the function because it just returned the number and it's gone. Unlike this memory grow here, then you see I modified the list, and the list it's bigger now, and I use more memory than before. And if I do it again, I append again, and it's getting bigger and bigger and bigger, and I get some growing data structure. So this is very simple code, you can see it, but if your program is more complex, you might have it somewhere when you're appending to a list, and for some reason you use the wrong name or something, and you're appending to a global list, and your memory is growing. So that's some place where things like this could happen. Okay. Maybe another interesting thing what I did with Pimple, I measured how the list is growing in memory if you append something. So that's a very simple simple code because it can be interesting. So that's a program called, what's it called? I didn't put the name. Yeah, list grows. Check the name. Pimple list grows, it's called. And then you can see measure how a list is growing. So I just write a function that takes the length of a list I want to create, and then I take a size function. And there are different ways to do it in Pimple. And you can have a size of and flat size, two different things to measure. One of them is measuring just the list as it is. The other one is measuring the list and the elements contained in the list. That's two different things. So the list itself takes memory, and the list just keeps the references to the other objects. And you might just want to measure the list itself, or you might want to measure the objects contained in the list also. There are two different things you want to measure. And you can use, one function is measuring the size of, the other one is the flat size. So it is the two different things. So check which one is which. So actually I do it here. I go through this different one. And those things come from Pimple, but they're very similar to this get size of. So Pimple is actually just using this built-in get size of, which you can use from Python. But for a few more difficult examples, difficult things like C extensions, they do something advanced. For this very example, the results are the same because it's very easy. And I just use my function here that's doing the same thing again, creating this list here, and you get this size of function, which is the memory you use, and then I append. So you see I go through and append, and every time I append, I measure how much memory it takes. So you see how the memory grows with appending things, and that's what I do. And then I have to make it nice, I just make a matplotlib picture and see how this grows. And so if you don't have matplotlib, it just prints out some numbers on the screen. If you have matplotlib installed, it will make a plot. So that's this thing. So if I run this, so you see how a list is growing in memory. So Pimple. Yeah. So if you do this, it takes a while to produce the figure, and hopefully it comes up after a while because it's measuring. This somehow it doesn't get a focus, so you have to click on here. Okay, you see, and now that's how a list is allocating memory. You see there's only the list. So it's not the elements in the list, it's only the list. And you see it's going stepwise. So it's always allocating more it needs for the next time. So even if you have a lot of elements, you only have to have very few allocations. So I think up to 10 million elements, you only have like 104 allocation steps, because every time it allocates more. And that's why the append is so efficient, because it has pre-allocated a lot of space already for new members. So every time you append something, it's there already, you can put it in, and then it makes one allocation again, and only very few even for large lists. So it is very interesting to see. You get a feel how things work, and it's pretty easy to do. For this one, you wouldn't even need Pimple. You could do this sysget ref count and just make a plot like this. Yeah. If you do the same thing with flat size, then this would be the next picture. Then you get a little bit different. Yeah, you get a very different one. Now I also measure the size of the integers. You see, the integers, of course, you will put more and more integers in, though you have much smoother growth. You still see the steps like a little bit here. That's where the list is growing. But now here, if you also measure the integer, then you see they are growing, and then there's a next step. But the integers all use memory. So that's a real memory usage you have. Okay. Yeah, and this is the same thing with sysget ref count. You see, it's exactly like the first picture, though in this case, this Pimple and sysget ref count. It's the same thing. Okay. That's it about measuring CPU and memory usage. I think this can be useful, and you can use some of the decorators, and you can since they are just pure Python, you can adapt the decorators the way you want. So if you want to do something different, you could. It's not that difficult. If you have some basic knowledge about decorators, you can adapt them, and you can also store it like I did in a global dictionary and get some things, and then you could some evaluation of your data. Okay, this concludes the section about measuring. I think that's maybe the most important thing. First, you have to know your system and see what's going on. And again, you have to be very careful every time you measure things to influence the system. So this one, that's why I do it 5 times to get back to 0 with Pimple, to get a real 0 count on those references, and then get the increase in memory. And if you use line profiler, you influence your system quite a bit. Okay, any questions about profiling, measuring things? Yeah.
So I have a question about the stats. So it's good that we have this picture on the wall now. Can you say something about the total time per call, come time, and something like that? Because I'm doing a lot of web development, and there is a suggest to order this by come time, and then to compare the difference between 2 lines. To find out which call is the most biggest or something like that.
Yeah, so the cumulative time is, of course. There are a few things. If you do this again, you might get some different results. That's the first thing. And you want to have the cumulative time you want it, because the time for one call doesn't really matter. You need, if a function is only called once and takes very long, it might not matter. But if you call it often time, then the come time it should be actually, if you multiply the times of calls with a time per call, there should be the cumulative time. In this case, we don't see it because everything is 1. So because you want to have the product of the times how often your function is called and how long it takes to call it once. That's what matters most, because it's the total time you spend on your function. Did I answer your question?
Yeah, I'm not really sure. I thought that the come time is the complete time the program runs. Is it incorrect?
No, that's a complete time it runs in this function. Oh, okay. So it's actually, if we have a different example somewhere, we should see. Whoops. Didn't I have it? I have it here interactively. So somewhere in the beginning you have this, you see 100 times per call, it's 0.001, and 0.001 times 100 is about the total time or come time. You see, in this case it's, Then I'm saying something wrong? Yeah. Yeah, so the come time includes the time spent in some sub-function. The total time, because you have the time you spend in the function, only in the function, minus the time you spend in the function you call, and come time includes the time you spend in the functions you call.
Yeah, and if you order this by come times, then you should see the first function call to the subcalls, right?
Yeah, because this big function call includes all the sub-function calls. Yeah. So the total time is it's time per call times n calls. That's the total time in this function, and the come time includes also the time spent in the sub-functions. So then you see that your main function should be the total runtime of the whole thing, come time, and then everything else gets broken down, and then you have this. Yeah.
Thanks.
Good. Okay, so that's the measuring part. I think we still have a lot to do. So we have 5 more minutes?
Yeah.
Yeah, 5 more minutes. So we want to use the time. And now, and pretty much, I think I go through this material here, because if I type, it takes a bit too long. But it shouldn't be that difficult. The next part is this micro optimization things. Algorithm and anti-patterns. I have a few things that you should know when you do things to make things easier. One of them is an old favorite, the string concatenation, which used to be very inefficient in older versions of Python. Newer versions of Python are pretty efficient, and also depends pretty much on the operating system you're on, how the operating system has handled its memory allocation, for instance. And now if I have a string like this, I can create a new string just by concatenating the thing. The thing is, if you do this, strings are immutable in Python. Every time you do something like this, you have to create a new string. That means you have to allocate new memory and put it in. So that's no problem for do it once. But if you do it with join, and see, next slide we have to jump now. If you do it with join, then it's pretty inefficient. And I hope I have this example. No, I don't have an example. So I just have to, seems like I don't have it written down. I have to show you what I mean. So I hope everybody knows join. Yeah. So if you do join, then you can join a list of strings into one string. So if I have a list of strings in this case, so if I have something like this, I have a list, and then in this list I have strings A, B, C, then you can join a list of strings and put them together. The other way would be write a loop and do something like this and say for x in my list ABC, for instance, and then the user plus equals, and this would make a new string all the time, plus equals x, and now you have the same result. But what happens here, every time you go through, you have to make a new string, because strings are immutable. You cannot add anything to a string. You get a new string and replace the old string with a new one, and every time you do this, you have to allocate memory, which is not a big deal if you do it a few hundred or a few thousand times. But if you do it a lot, then it might be a problem, because you always have to do this. Though the easier ways would be just join, collect everything in a list, and then at the end do join. This is a more efficient thing, because I showed you the list is growing this memory stepwise, so you have very few allocations, even if you have a very big list. So if you try this on a Linux or Unix or Mac system, you won't see a big difference. If you do it in Windows, you will see a different result, because the operating system is the memory allocation in Windows works differently. So especially in Windows, if you have big lists, you will see like a difference between 5 or 10 using big lists in terms of runtime. In Linux, usually there's no difference. So it depends on your operating system, but still you don't know. But if you write something what operating system people use, so that's one of the small anti-patterns. But it's much more mitigated over the last versions of Python. Used to be in 2.5. There used to be, or 2.4 used to be much bigger impact. Now it's this new versions of Python, because it's a common thing, and they kind of optimize this out for you. So it's just one of those small things. So sometimes it can also be nice to just use a list for strings, because you can append, you can change things easier than always working with a big string. Sometimes depends what you're doing. Okay, the next thing is generators and iterators. So lists and generators, generator comprehensions. Probably everybody of you knows list comprehensions. So we can use list comprehensions, which is very nice. So you can do something like this. X range 10. So this is a list comprehension. Sometimes you just want to have a sum of this one. And if you do something like this, then it works very nicely. But this would be kind of waste of memory all the time, because what you do now, here you generate an intermediate list, and you don't need to do this, because you can use a generator instead, because you don't do anything with the list anyway. So it's very easy. You just get rid of the brackets here, and then you do sum, and you get the same result. And this is just generator and generator expression, and generator expression is just generating one element at a time. So if you run this to this Pimple memory measurement, you'll see this one will use just very little memory, no matter how big you do this here. If you use X range in Python 2, yeah. If you do this one then the bigger this number gets, the more memory you need. And if you don't need the intermediate list, don't use it. Yeah. So list comprehensions are very nice, but this is even shorter. Just you don't have the brackets there. That's every time you don't need the list. If you want to sort something, you need a list. And there's no other way to sort it. Or if you want to work later on, you want to access it with indices, then you need it. But if you do something and you don't actually need the list, it's highly recommended to use generator expressions. So it's a bit faster, and the readability is the same. So that's one of those things. And it's a micro-organization, but it's a good one because it makes sense. And if you work with Python 3, you will see this more and more. A lot of built-in functions return iterators or generators instead of lists. And if you want to, you can always turn them into lists just by calling list. So that would be something again. I have one small topic. So should we? 2 more minutes, or
yeah.
So I think we have one small topic that I would like to finish, and then we have a break. And this is about global versus built-in. So I have a small example here where I use a global variable. Very similar to the other one. I have a global variable here, and I access this global variable from inside the loop, or I just make this global variable local in front of the loop and then access it. And then I just use my C profiler and run this thing for 100 million times, and then just print the stats. Let's do this quickly. So it's just the difference between local, global, and then you run it, and then you will see a difference. I don't know, 100 million times. Suppose I don't do a lot. I just access this variable. Do you see the difference now? And again, where are we? Here's a repeat local takes about 4 seconds, and the other one takes about 9 seconds. So sometimes if you do something do a lot of lookups, then every time you do this, Python has to go in here and say, okay, this global, where does it come from? Is this a local? No. I look it up, it's not. Then I have to go to the global namespace. If I find it there, it's okay. It's additional dictionary lookup. So you have 100 million more dictionary lookups, and that might take time. And if you have a deeper nested thing with a lot of dots, then you do even more lookups. And very similarly, you can do this built-in one, which is even more expensive. So now you see, I use just access true, and here I just make a small trick. I call this true, and this is even more because here I can use a local. This one has to look in local, it's not there. Has to look in the globals, it's not there. Has to go to the built-ins. There's another lookup, and when you run this, then you see even a bigger difference. So it takes also about 15 seconds. So this might be worth it. So if you profile, you can test it to make things local. And sometimes it can be useful if you just rename things and give it a more descriptive name. It might be also better for your code. So you see it, and this again, now we have 4 seconds versus like 11, 10 seconds. So it's a bit different. Not so big difference as there, but there are some difference going to the built-ins doing this. So that's some small micro things you can think of, and if you do it right, it doesn't make your code more difficult to read. Okay, so we finished the section about this algorithmic things. We have a break now. So official break is like 45 minutes to 11:15. Yeah. So,
but you can decide otherwise if they are going to do something. So if you want to finish earlier, for instance, or whatever.
No, I think we have plenty of things to cover. So if you want to come a bit, who wants to take the full break? Who wants to come 10 minutes earlier? Who wants to finish full break? 10 minutes earlier. Okay, then we start 5 past 11. 5 past 11. So we have gained 10 minutes.
Okay. Like yesterday, we are going to be around here, so if you want to leave your laptop or stuff, we are going to have a look at the room while you are at the coffee break.